Okay, good morning all. So started with one of the problem on frame analysis yesterday, and the frames what we are taking up now are all non-sway frames. Later we'll deal with the sway type of frames. So have you gone through that yesterday's problem? After that, after the class, if you have any problems solving such frames or in any part of the problem. And what we'll do today is we'll again continue with the frame problems. Okay, so and this was the problem what we had taken. Okay, and we have plotted the bending moment diagram and the deflected shape finally after solving it by slope deflection method. So continuing with that, this is the second problem. Okay, and here is the frame. Okay, so you need to analyze this, draw the bending moment diagram and the deflected shape for that, and using the slope deflection method. Okay, so if you calculate the degree of static indeterminacy, it is coming out to be 4. So I have two fixed support here, 3 reaction at this support, 3 reaction at this support, and 1 roller support at B, which will offer 1 reaction. So 3, 3, 6 plus 1, 7, minus 3 conditions of equilibrium. So that will give us the degree of static indeterminacy, 7 minus 3, 4. Okay, and in slope deflection method, it is mainly the displacement based method because we are treating displacements as our unknowns. In our equation, we are coming across theta and delta. They are displacements. So what we will be looking for is what is the degree of kinematic indeterminacy mainly. Okay, if you want to know what is the degree of kinematic indeterminacy, rotation at B and C, they are the unknowns. So degree of kinematic indeterminacy will remain 2. Okay, so eventually we'll get equations in terms of two unknowns in slope deflection method, which will be solving them by taking help of conditions of equilibrium. Okay, so you have to keep in mind that how to calculate the static or kinematic indeterminacy. Without that also you can solve the problem, no doubt, but it is a good practice that you know how you can determine the static and kinematic indeterminacy. That will tell what are the unknowns in your frames or any structure. Okay, so I would have calculated that also. That is actually the main important point, kinematic indeterminacy. So have a practice of determining those indeterminacies. Okay, so to begin, what we have to do here is we are always starting with the fixed end moments. These are the quantities which will come in our slope deflection equation. I have written the slope deflection equation here. Okay, Mij at any joint, the moment Mij is equal to Mfij, the fixed end moment at that joint, plus 2ei by L into 2 times theta I plus theta j minus 3 delta upon L. This is our slope deflection equation. So we need to substitute for these quantities. Some values may be known to us and some may be unknown. Okay, we have to determine the unknown values, okay, in this process. So first we'll go ahead with calculating the fixed end moments. So one of the member, which is this member BC, I have taken that first. I have not shown the calculation. Actually, the problem is very lengthy. Okay, I have the rough calculation with me, but I have not shown it here. Okay, in order that it will be clear for you people to understand the problem. Okay, you have to practice that. I am sharing every problem after the class. So what you have to do is you need to practice the uh, problems. Okay, or else it will be very difficult for you to solve them at once. So here, if I take the member BC, so it is carrying UDL for its entire length. In such a case, the fixed end moment magnitude will be WL square by 12. Okay, so at this end B, moment or the fixed end moment will be in anti-clockwise direction. I have used negative sign for that. So MFBC comes out to be minus WL square by 12. And this, on substituting the value, what is the span here? 3 meters. W intensity of load is 20 kilonewton per meter. So that has been substituted. And value of MFBC is minus 15 kilonewton meter. Okay, minus 15 kilonewton meter. That is the value what you come across for MFBC. Similarly, when I go for determining MFCB, fixed end moment at joint C in member BC. Okay, at joint C in member BC, here it will come out to be in clockwise direction. Okay, so direction is clockwise. What is the magnitude? WL square by 12. So plus WL square by 12. Since it is clockwise, plus, and magnitude is WL square by 12 for a member carrying UDL for its entire length. Okay, so here value comes out to be plus 15 kilonewton meter. Okay, this is for member PC. We are done with calculating fixed end moment at both the joints. Now one more member what we have is CD. Okay, what is that CD? CD is a member of length 4 meters and it is supporting a concentrated load of 50 kilonewton at the midspan. Okay, exactly at the midspan. Okay, there is a load of 50 kilonewton, point load of 50 kilonewton meter, sorry, kilonewtons only. So in that case, the fixed end moment, it will be WL by 8. Okay, so you need to assign the sign, you need to identify the sign under such a circumstance. So at this joint, the moment will be anti-clockwise, and over here, the moment will be clockwise. Okay, so it depends on how the load is acting on the member. Okay, so these fixed end moments are the reactions actually. So they will be opposing the moment due to applied load. So these are the directions what you will find at the two ends of this member BC. Okay, so you will have to look into those and assign the proper sign for them. Okay, so here I use that sign at joint C in member CD. Okay, what I have at joint C minus WL by 8, and that comes out as minus 25 kilonewton meter. Similarly, at joint D in member DC or member CD, it will be plus WL by 8. Okay, the magnitude will remain same, only the sign, what will happen to the sign is at this end, moment, fixed end moment which will be developed at joint D will be in clockwise direction. So we'll be taking the positive sign for that, plus 25 kilonewton meter. Okay, so member BC and member CD, we have calculated the fixed end moment. Now with this vertical member, this CE, for this, what we have here is there is no load which is applied on this member. So there is no question of any fixed end moments coming at the two joints on the member CE. So MFCE as well as MFEC, they will be 0. Okay. So these are our fixed end moment. That completes the calculation of fixed end moment. Now they will be used in our slope deflection equations here. Okay. When I go with member BC, okay, I can write the slope deflection equation by replacing this I and J by B and C. Okay, so MBC will be equal to MFBC plus 2EI by L into 2 times theta B plus theta C minus 3 delta upon L. Okay, so this entire equation will be applying it for the member BC. The respective I value and L value, whatever is the I value and L value for this member BC will be substituted in this equation over here. Okay, the fixed end moment for BC, the moment of inertia value of span BC, the length of span BC will be used in this. Okay, so that has been substituted. And what about these terms? These are the displacements now, rotation and if any settlement, if they are taking place, have to be substituted in this bracket. So we don't know what is theta B and theta C. They are the unknowns for us. We need to determine them. Okay, so they are kept in terms of unknowns as theta B and theta C. Now delta, we don't have any settlement given to us between B and C. There is no settlement that is taking place. Okay, so this delta term will turn out to be 0 here. Okay, so when I put these values, when I use them, the simplification, okay, it gives me this equation. What it is, MBC will be equal to minus 15 plus 4EI by 3 into theta B plus 2EI by 3 into theta C. Okay, I is constant for entire member. Okay, for this member. L, what we have is the span is how much? It is 3 meters. So that has been substituted. So this is the first equation what we will come across. Okay, on substituting the values over here, fixed and moment values and other values. So let us say this is equation number 1 in our case. Okay, now same, I'll repeat it for what? Member BC from end C, from joint C. We have written the slope deflection equation with respect to joint B. That was MBC. Now I'll take the same member BC. I'll come to this joint C. For this joint and for member BC, I'll write the slope deflection equation. Okay. So now the same general equation will be considered. I and G, what they represent now? They represent C and B. Okay. I'll be considering I as C, J as B. Okay. The near end and the far end. I'm at joint C. So C will be my near end. B will be my far end. That is how we understand this equation. Okay. So MCB will be equal to MFCB plus 2EI by L, okay, into 2 times theta C, okay, plus theta B minus 3 delta upon L, okay. So that is how you need to substitute. L, it is again 3 meters. I is constant, okay. It is simply 1I. So after substituting, what we have is, this is the second equation, what we get on simplification. MFCB 15 kilonewton meter, so that is here, and 2 EI by 3 into theta B, okay, this one, plus 4 EI by 3 into theta C, and this delta term is 0. Again, we don't have any relative settlement between B and C, so delta is 0. Okay, so this will be the equation, form of equation. Okay, so this is the second equation of slope deflection. This I have arranged them alphabetically so that it will be convenient to solve later. Okay, only that is the difference. So this is the slope deflection equation for BC, member BC. We have considered both the joints and we have written two equations for each joint. So these are the two equations, 1 and 2 for member BC. Now moving on to the next member, what we have, okay, immediately if I take this vertical member over here, I have to write the equation for MCE and MEC, okay. One slope deflection equation at joint C and another slope deflection equation considering joint E, okay, for member C. So that has to be done. Fixed end moments for that member, they are 0. It is not having any load on over it. Okay, so fixed end moments are 0. Now let's see what is the equation we will get. So here theta E is taken 0. Why it is 0? At the base, at the end E, we have the fixed support over here. Okay, so you have the fixed support here. It will not allow any rotation, any kind of rotation. Because of that, rotation at E, theta E is taken 0. It will be 0 because of the fixed support. And fixed end moments, we calculated them. Since there is no load, that MFEC and MFCE both are 0. Okay, now what happens? MCE, if I consider MFCE 0 plus 2 EI by L, L is 4 meters, into 2 times theta C plus theta E will become 0. This will be theta E minus 3 delta upon L. This term will also vanish because no settlement. Delta will be 0. So this will vanish 0. This is also 0. Simply I'll be left with 2 EI by 4 into 2 times theta C. Okay, that will be 4 EI by 4 into theta C. Altogether, what we come across will be EI into theta C. Okay, MCE will be EI into theta C. This is the equation of slope deflection for member C with respect to joint C, for member CE with respect to joint C. This is the third equation. Okay, and same when I come with the joint E. Okay, coming to joint E and for member CE only. Okay, there what I have fixed end moment. When I write the equation, it will be MEC, okay, which is equal to MFEC, which is 0, plus 2EI by L into 2 times theta E plus theta C minus 3 delta by L. Okay, which all terms are 0 here in this? When I write that equation, MFEC is 0. Okay, this 2 times theta E will become 0 there, and this delta term is 0. Okay, so what I'll be having is 2EI by 4 into theta C. That's all. I'll be left with 2EI by 4 into theta C. So that will be EI by 2 into theta C. This is MEC, which is EI by 2 into theta C. Okay, so these two equations, how we got them is by writing the slope deflection equation for member CE at joint C and at joint E. So it is giving us another two slope deflection equation. Okay, so 3 and 4, we'll call them as equation 3 and equation 4. Now what is the last member here in this frame? This member CD. Okay, we are done with BC, we are done with CE, and member CD is left out now. Okay, so for CD, I have the fixed end moments because there is a concentrated load which is there on this member. Okay, the span is 4 meter. So what is the fixed end moment? Minus 25 and plus 25. These are our fixed end moment which we have calculated. So this equation, how you are going to read it now? I'm dealing with member CD. Okay, so MCD, IJ will represent now C and D. MCD will be equal to MFCD plus 2AI by L into 2 times theta C plus theta D minus 3 delta by L. Okay, so again observe the frame. What are the conditions at joint C and D? C is allowed to rotate, so theta C will exist over here. It is unknown, it will be there. Okay, we have to find its value. At D, what is this condition here? The support is there, and that is a fixed support. It is a fixed support at D, so no rotation is allowed at joint D. Okay, so theta cannot exist at joint D. That indicates theta D is 0. Okay, also delta is 0. There is no relative displacement of joints C and D. Delta becomes 0. Theta D is 0 and delta is 0 in this member CD. Okay, so keeping that in mind, I'll substitute the values. Okay, so what happens? MFCD minus 25 plus 2EI by 4. Okay, span is 4 meters, 2EI by 4 into 2 times theta C plus this is 0, this is 0. What it gives us? Minus 25 plus 2EI by 4 into 2 times theta C. Okay, that is minus 25 plus EI into theta C. Okay, if you simplify this term after multiplication, it will just give you EI into theta C, right? So this is the fifth equation of slope deflection for member CD and at joint C. Same for member CD. When I move to joint D, what will happen to this equation now? MDC will be equal to MFDC plus 2EI by L into bracket 2 times theta D plus theta C minus 3 delta by L. Okay, so here what are the 0 terms? Theta D is 0, so this 2 times theta D will become 0. Delta is 0, so 3 delta upon L will become 0. I'll be left only with 25 plus 2 EI by 4 into theta C, 2 EI by 4 into theta C, 2 EI by 4, which will be EI by 2 into theta C. Okay, so this is what I have, MDC. So there are totally 6 slope deflection equation, 2 for each member. We have 2 joints in one member, so we have written 2 slope deflection equation for each of these members, member BC, CE, and CD. Okay, 6. Now from these 6 equations, we have to obtain the value of theta B and theta C. How we can do that? 2 unknowns, 6 equations. Okay, so for that, what we'll consider is our one more conditions. What are the next conditions we have? Conditions of equilibrium. Okay, what are the conditions of equilibrium? You have to satisfy the conditions of equilibrium at each of the joints. So here what I have is at joint B, okay, MBA plus MBC. Okay, MBA and MBC should be 0. When you add them together, that should come out to be 0. So how do I find this MBA? Okay, so actually what was there is at joint B, two members were connected at joint B. Okay, so here BA is one member and BC is another member. Okay, so what we have neglected this member BA, which is a overhang portion over here. Okay, because I can replace this entire overhang portion by a force and couple, equivalent force and couple at joint B. I can bring this 20 kilonewton force over this joint B along with the couple over here. Okay, so I can do that. So I don't have to deal with this member BA. Okay, it is just a overhang portion, and what is happening is due to this overhang portion, there is a moment which is applied at joint B, which is of 20 into 1. 20 kilonewton meter is the moment which is applied at joint B. Okay, so with that, applied moment is 20 into 1, 20 kilonewton meter, whereas the reaction from due to that MBA will come out to be here, sorry, 20 into 1, okay, 20 kilonewton meter, and it is in anti-clockwise direction, and the reaction over here will be clockwise. Okay, that is MBA. That itself is our MBA. Okay, is that clear? Writing the slope
Yes, sir.
deflection equation, we are done. Okay, and the member BA, how we are going to take care of that overhang portion. Okay, that will be treated as a applied moment on joint B. Okay, what is the direction of applied moment? 20 into 1, 20 kilonewton meter in anti-clockwise direction. Okay, at this point, the moment due to 20 kilonewton meter will be anti-clockwise. Okay, this will be having an anti-clockwise moment, and the reaction for that will be in clockwise direction, which itself is our MBA. Okay, so that is how you get to know what is MBA over here. Okay, so now let us take that value in this equilibrium condition. What is the equilibrium condition I had here? MBA plus MBC is equal to 0. So MBA 20. Okay, this is a reaction at this fixed end. You can look at this as a cantilever beam. So what is the reaction here is opposite to this applied moment. So 20 clockwise moment, MBA 20 plus this was our equation number what? 2. Okay, equation number 1, I think, not 2. This one, MBC, we had it here, minus 15 plus 4 EI by 3 theta B plus 2 EI by 3 theta C. Okay, the same equation I have used here and simplified this. So on simplification, so rearranging the terms. So what it has is actually 20 minus 15. So it will come out to be 5. I've taken the 5 on the other side, multiplied the entire equation by 3. So it will result in this simplified equation number 7. It is 2ei theta b plus ei theta c, which is equal to minus 7.5. This is one equation from condition of equilibrium, what we got from condition of equilibrium. We have made use of our slope deflection equation, what we had in this condition of equilibrium. Okay, so like this, we have one more condition of equilibrium at joint C. There is another joint, which is joint C, this one here. So three members are connected at this joint. Okay, BC, CD, and CE. Okay, three members, CB, CD, and CE. Three members are there. So when you add up the moment due to all these three members, whatever the moment is developed at joint C due to all these three members, that should result in 0. Okay, so that has been expressed here in the second condition of equilibrium. At joint C, these are condition of equilibrium. At joint C, MCB plus MCD plus MCE should come out to 0. Okay, we had already this equation 2, okay, and equation maybe 5, and like this. So I have made use of those slope deflection equation in this. So MCB is 15 plus 4 EI by 3 theta C plus 2 EI by 3 theta B. Okay, this is MCB plus MCD is minus 25 plus EI into theta C. Okay, if you look into those first 1 to 6 equations, from there itself I have taken this equation. Okay, MCB, MCD, and MCE. What is MCE? EI into theta C. Okay, so here we have those equations. MCE EI into theta C. Okay, MCB 15 plus 2 EI by 3 theta B plus 4 EI by 3 theta C. Okay, and one more CD minus 25 plus 2 EI theta C. These equations have been substituted over here. And on simplification of this, okay, second condition of equilibrium, you get this equation number 8. EI into theta B plus phi EI into theta C is equal to 15. Okay, so that has been simplified. Okay, just by taking some terms to the right hand side and unknown terms I have kept it on the left hand side. Like that I have simplified these equations 7 and 8. And now solving these two equations, they are simultaneous equations, two unknowns. So when you solve them, theta B comes out to be minus 5.833 over EI, okay, which is anti-clockwise rotation. It is an anti-clockwise direction rotation. And theta C is 4.167 over EI. This is a clockwise rotation. Sign R indicating me whether the rotation is clockwise or anti-clockwise. Theta B is having negative sign, so it is anti-clockwise. Theta C is having positive sign, it is clockwise. Okay, now what you have to do, you have to use this value of theta B and theta C in equation 1 to 6. Okay, if you just put these values in those 1 to 6 equation, you'll get to know what are the moments at the joints. Okay, AB is a free end. Okay, so eventually the moment is 0 there. Okay, I have the moment 0 at that free end. So I have taken that 0. Further, I used this one. MBA was also determined. It was 20 km clockwise. When I use theta B, theta C in MBC, what I come across is minus 20. Okay, plus 20 minus 20 at joint B 0. Okay, so that is the condition or the verification what you have. Similarly, the other moments we can get using this value of theta B and theta C. Okay, MCB is coming out to be 16.667, CE 4.167, CD minus 20.833, DC 27.084, and EC 2.084. Okay, so you have to just use these two values of theta B and theta C in equation 1 to 6, wherever they are applicable, there you have to substitute them. Okay, you'll get to know all the values of bending moment, joint moments. Okay, bending moment at the joints. Now, once we have the values, okay, what we have to do is plot the bending moment diagram. Okay, so this is the bending moment diagram. At A, MAB was 0. Okay, ordinate is 0 here. At B, MBA was 20 kilonewton meter. I have taken an ordinate of 20 kilonewton meter here. Similarly, at joint C, MCB, it was 16.667. So that is the ordinate for MCB. This is the ordinate for MCB, short order ordinate. And MCD, it was coming out to be 20.833. So this is the ordinate for MCD. This longer ordinate is for moment MCD. And at D, it is 27.084. Okay, accordingly, the ordinates have been plotted here. Okay, so just connect the tip of these ordinates by a straight line. Okay, so that will give you the moment at the joints. Over that, free bending moment diagram has to be overlapped. Okay, BA WL square by 8, which gives you 22.5 as the maximum moment at the center. And for this, it is WL by 4. So this comes out to be 50 kilonewton meter as the moment in the span. Okay, so that is for the two members or the three members beams. Now for column, I have told you, look into the movement direction, what is applied over there. So CE and EC. I want CE. CE is clockwise. Okay, magnitude we'll plot them, no, not a problem. CE is clockwise. EC is both are clockwise. Okay, CE and EC both are clockwise here. If you can see, CE plus 4.167, EC plus 2.084. Both are clockwise. Now for plotting this, so this is the clockwise moment over here. So I have the clockwise moment applied at CE. Okay, so this is the clockwise. So what is the direction of bending? Towards left. I have plotted the ordinate towards left. Okay, now in this here the moment is again it is clockwise. Okay, so here the bending direction is towards right. Both are clockwise movement, but they are trying to bend the member towards left about joint C and towards right about joint E. So from that, I have taken these ordinates. You have to apply that movement exactly at that joint. See in what direction it is trying to bend that member. In that direction itself, you can plot the ordinate, okay, and assign those values. So that is a bending moment diagram for that vertical member CE, okay. And then later what we have to do is plot the deflected shape. This is the deflected shape. This you have to plot it, okay. So here entirely it is sagging. In member AB it is sagging. From A to B it is sagging. So curvature will be upwards. This is the sagging this one shape over here, okay. I have not got exactly the curvature, but it is bent in such a direction that curvature is upwards. And here again curvature is upwards at joint B. You come across sagging movement in this portion. So this is sagging, sorry, hogging. I'm sorry, hogging. Please note that. And when I come to BC member, in the middle portion, I have the sagging moment, positive. This is sagging moment here, okay. And similarly at joint C, you come across hogging portion, point of contraflexure. Beyond that, there will be sagging bending, okay. And again here curvature will be upwards towards D, hogging, okay. Here bent towards right, left, okay, curvature towards left, and here curvature is towards right, okay. Here you will not come across any slope because these two are fixed support, so slope has been maintained 0 here, okay. You can approximately draw this deflected shape, okay, not a problem. You don't have to worry much about this, but approximately it should resemble some behavior of the frame, okay. Like that you have to draw it. Other than that, bending moment diagram you should be able to draw it correctly, okay. Some variation in the deflected shape is okay, not to worry about that, okay. So these are the two diagrams, one this one and two this one, okay. So these two have to be plotted after you calculate the bending moments. Is that fine?
Yes, sir.
Anybody with problems, difficulties, facing any difficulties, not understanding that? Okay, you have to go through this. Once I complete the class, I'll pass on this solution. See that you do the calculation, sit with the calculator, verify whatever values are written here, try writing the equations, okay, in a complete form. I'm not given in a complete form. I have them, I have solved, but I want you people to write them with reference to this equation, write completely. You are expected to do complete calculation in your examinations, not just simply putting these final form, okay. So try to do that, okay, and see that you are able to solve it, okay. Right. I'll just take one more over here about same about the uh, frames. Just 2 minutes. If you have anything, I have some correction in that frame. Just think about that previous problem. Any difficulty in that part, I want you to come over here. Okay, shall we move ahead? always you will be dealing with those slope deflection equation throughout this module. Okay, and every time the slope deflection equation requires you to find out the fixed end moments, write the slope deflection equation for each of the member and at each joint, then apply the condition of equilibrium and obtain the unknown displacements in the frame. Okay, so this is one more example over here. Okay, so this is a frame. What you have, there are two horizontal members, AB, BC, and AD and B are the two vertical members, the columns. Mainly they are the columns. So here, this member AB is supporting UDL of 40 kN and it is having a moment of inertia of 2I. Similarly, AD is having a moment of inertia of 2I, whereas member PC is having a concentrated load of 80 kN over on it, okay, at a distance 1 meter from support C, and it is of 4 meter spans. B is having 3 meter span and I value is 1I. Okay, for BC and B, I value are 1I. Okay, sometimes there will be variation in this I, so you need to take care that you substitute them properly whenever it is changing. Right. So these are the moments, fixed end moments, what you have. Okay. So yes. So anybody having the problem? Please mute yourself. Okay. So the first step, it is done. What is there? Calculation of fixed end moments. Okay. So only thing is for this again it is WL square by 12, anti-clockwise at joint A, clockwise at joint B. Okay. For BC, what you have? Okay, what is the MFBC? It will be in anti-clockwise direction. Value will be minus WAB square upon L square, minus WAB square by L square. So this is not a load which is applied at center. Okay, it is not at the midspan. It is at a distance 3 meter from joint B and 1 meter from joint C. Okay, so A is 3 and B is 1 meter. That is what is considered here, AB. Okay, MFBC minus WAB square by L square. This is minus 15 kilonewton. MFCB WAB square by L square. Okay, you need to remember these formulae of fixed end moments. Okay, there is no other way for that. You have to remember them. Okay, deriving them and all is not possible in your exam or for you. So you have to memorize them, remember them. MFCB is WAB square by L square clockwise. So that comes out to be 45 kilonewton meter. Okay. Other than that, on these two members, AD and BE, moments are zero. Fixed end moments are zero. AB, it is minus 120 plus 120. At A, it is minus 120. At B, plus 120 kilonewton meter. Okay. This is the fixed end moments. Now, if you look at static indeterminacy, what you get is 3, 3, 3, 9. 9 support reactions, unknown support reactions, minus 3 conditions of equilibrium. It will tell that degree of static indeterminacy is 6. Kinematic indeterminacy, can anyone tell me what may be the kinematic indeterminacy in this frame? Degree of kinematic indeterminacy, which is actually tell you how many unknowns will be there in the slope deflection equations. That kinematic indeterminacy will tell you that. So what you have, joint A and joint B displacements are allowed here. So both are allowed to rotate. So theta A and theta B will be the unknowns. The kinematic indeterminacy is 2. The degree of kinematic indeterminacy comes out to be 2. They are theta A and theta B unknowns. Okay, so we'll have slope deflection equations in terms of theta A and theta B only. Okay, so also this is a non-sway frame. due to presence of this member PC, which is connected to that support C over here, this sway has been prevented. It will not sway over here. Okay. First is you should make that clear. What is a type of frame, whether it is a sway frame or non-sway frame. And the equation what you have for slope deflection, I have taken that again, Mij, which is equal to Mfij plus 2ei by L into 2 times theta I plus theta j minus 3 delta upon L. Okay. And what are the zero terms here? Delta. No delta exists in our frame. Settlement is not there. So delta is 0. Okay. Or sinking is not given. And also the rotations. Let us look into these joints. D is fixed, E is fixed, and also C is fixed. All these three joints, D, C, and E. Okay. These three joints are provided with the fixed support. For that purpose, the rotation at these three joints, okay, theta C, theta D, and theta E will remain 0. Okay, there will not be any rotation at these three joints. So you can take them to be 0. Okay, so these are the 0 terms that have been identified here. Other than this, theta A and theta B will exist, and we have to determine their value. So applying the slope deflection equation, okay, what I come across is MAB. Okay, so here it is given here. So on simplification, MAB is minus 120 plus 4ei by 3 into theta A plus 2ei by 3 into theta B. I've used this equation, substituted for the MFAB, span of AB, and I of AB, 2i. It is 2i here. Okay, so it is varying I value for all the members. Okay, so here we have the first equation of slope deflection for MAB, or for member AB at joint A. Similarly, for member AB at joint B, what I come across is MFAB plus 120 plus, by simplifying, we get 2ai by 3 into theta A plus 4ai by 3 into theta B. So that is the second slope deflection equation. Okay. And next member, if you consider this, what is that? BC. Okay. So MFBC minus 15. So minus 15 plus 2ei by 4. 4 is the span of that BC, member BC, into 2 times theta B plus theta C. Okay. So if you simplify that, this is what MBC will be minus 15 plus EI into theta B. Theta C is 0. We have noted this. Theta C is 0. Okay. MBC is this equation. Okay. MCB, what we have, MFCB is 45 kilonewton meter plus EI by 2 into theta B. Okay. Theta C is 0. What we have is, in that case, 2 EI by 4 into theta B plus 2 times theta C. Theta C being 0, so it will vanish out. We'll be left with MCB equal to 45 plus EI by 2 into theta B. So this is the fourth equation of slope deflection, what we have here. Okay. Now for AD, member AD, vertical member, the fixed end moment is 0 there. Okay. MFAD was 0. And 2 EI by L. What is the I value for this AD? It is 2I. So 2 EI by 4. Okay, this 2I has to be considered. 2 EI by 4 into 2 times theta A plus theta D. In this, theta D is 0. Okay, theta A exists. So what you have, MAB is simply 2EI into theta A. Similarly, for MDA, it will be MFDA plus 2EI, that is 2 into 2I by 4 into theta A plus 2 times theta D minus 3 delta by L. On considering all the 0 terms, finally MDA will be EI into theta A. This EI into theta A. This is MDA. And BE, another member is this member BE. So what we have for member BE, span is 3 meter, I is 1I. So MBE is no load, MFBE will turn out to be 0. 2 EI by 3 into 2 times theta B plus theta E. Theta E fixed end, so this is theta E is 0. So it will be simply MB equal to 4 EI by 3 into theta B. And MEB, if you work out on the same basis, it will come out to be 2 EI by 3 into theta B. MPE, moment at joint B for member B, joint E for member BE. Now I'm considering the condition of equilibrium. What all condition of equilibrium exist here? We have two joints in this frame, A and B. Okay, so movement about joint A should be 0, and movement summation of movement about joint A should be 0, and summation of movement about joint B should also be 0. So that is what I have done here. MAB plus MAD, okay, MAB plus MAD should come out to 0. MAB and MAD should come out to 0. At joint B, what you have? MBA plus MBC plus MBE. So when you add these three movements, because three members are connected at joint B, when you add up these three movements due to the three members, so that should come out to 0. Okay, so substituting for these, okay, MAB and MAD, they are in terms of slope deflection equation, what we have written from 1 to 8 over here. Okay, they'll come in those equations. So on substituting, you will again get an equation in terms of unknowns only. That will not directly solve your equation and give you unknowns. Okay, these conditions of equilibrium may result in some more unknown equations. Okay, like this. So when I take this first condition of equilibrium, it is giving me a equation 10ei into theta a plus 2ei into theta b is equal to 360. Okay, that I would call it as equation 9. Similarly, when I take the second condition of equilibrium, MAB plus MBC plus MBE is equal to 0. So that is resulting in another equation in terms of theta A and theta B only. Okay, so 2 times theta A plus 11EI theta B is equal to minus 315. Okay, just you have to rearrange the terms in this. Known terms on one side, unknown terms on other side. That has been taken over here. And after this, finally, what we go for is solving these two equations which we get from the condition of equilibrium. So when I solve them, theta A 43.30 over EI, that is the value of theta A, clockwise rotation. Theta B minus 36.51 over EI, anti-clockwise rotation at B. So these are the values of displacement at joint A and B. Okay, theta A, it is rotated in clockwise direction. Theta B, joint B is rotated in anti-clockwise direction. Values are here. Okay, so you have to put these values in these equation of slope deflection to get the moment values. So these are the values of moment, what you obtain. Theta values, it will be representing A and B over here, B and A and B like that. Okay, so when you substitute them for thetas in this equation 1 to 8, these are the moments what you come across, bending moment at those joints. Okay, using these bending moments, okay, you need to follow the same procedure what I have explained earlier. Okay, so for beams, there's not a problem. You'll be drawing the ordinate, okay, in vertical direction above that beam line, center line. Okay, and then you connect them by a straight line. That will give you the support moments, variation of support moments in the beam. Okay, over that, overlap the free bending moment diagram. That is what is done here. For the columns, just look for the direction of the movement. Say this was member, what was this member? AD. Okay, so MAD is 86 clockwise. So this is clockwise. About this joint D, apply about this joint A. I'm taking AD. I'm at joint A. So here I have applied a movement in clockwise direction. When you apply it, it will try to rotate this member towards what? Left. Okay, this is our joint D. Here I have applied the clockwise movement. It will try to bend this member towards left. So ordinate is taken towards left. And what about DA? It is also clockwise, 43.30. So clockwise movement at joint D. Okay, so this is clockwise movement over here at joint D. It is also bending, it is bending the member towards right. So ordinate is taken towards right. Okay, that is how the ordinate is decided. So, and then these bending moment is variation of bending moment is plotted for these vertical members. Same for this. Okay, also check, you can observe MAB plus MAD should come out to 0, minus 86.61 plus 86.61 at this joint. So it comes out to 0. BA plus BC plus BE should be 0. So when you add these values, minus 51, minus 48, so nearly it is coming out 99. Okay, so almost 0 here. adjoint B also. That is should be the check for you. Okay, so that is the plotting of bending moment diagram. Okay, please go through these. Okay, just listening will not help you. Go through all the three problems. All are on non-sway analysis. Okay, and understand this procedure as well as solving the problems. Okay, work on these problems. Other than that, if you have any problem, other difficulties, you can come up with them at any time. You can post them in your group, okay, or even in the class, you can try asking them. Is that okay?
Yes, sir.
Others, I don't know whether they are there. Mobile may be online. What about yourself?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So three problems what we have dealt now, okay, try solving them, all the three. Take the same problem, try to write this equation, simplify them, okay. You'll get stuck up, okay. It appears to be very simple looking at this screen. This is the final solution what I have put over here, okay. There is a lot of rough work what is there. So you'll come across mistakes while solving the equation, while writing the equation, okay, that happens. So you need to practice them so that you'll come to know where I can go wrong, okay. So that the same three problems on frames, okay. Don't look at this. If you have understood the problem, try solving them. If you have any difficulties, just you can this will serve as your reference. You can go through this and try solving that, okay. So try that one. And after that, if you have any problems, you can just chat in your group or in when you are on online class also, you can put that, okay. So we'll finish that, and we'll see in the next class about the other problems.
Okay, sir.
Okay.
Okay, sir.
You can leave.